this first example, okay, we have a steam that is generated at this pressure, 4.10 MPa, and 440 degrees Celsius. And then condensation occurs at 0.105 megapascals. Okay. So since these are the only three, I know we're assuming that this should be an ideal cycle because we cannot really get a lot of information here. We are going to assume that this is just an ideal Rankine cycle. So it is usually simple, it is just an ideal Rankine cycle. So we can draw the TS diagram here. So we have two working pressures. The higher pressure is 4.10. So this is the constant pressure heat addition. And then you have also the constant pressure heat rejection. So we have 4.10 and 1.1. Now to make things a little bit quicker, I already found or I already done the solution of this. Because it really takes a long time to find the state table properties and then teaching law. So I just solved this and I'll just explain how I found the properties and where should you start. So it really depends on the problem. No? So the problem here is we want to find the heat addition, no? QA, heat rejection or the network, W net, and the cycle efficiency. No? So basically, if QA is only the one that you want to find, you just find each one, no, and then each week. You can actually do that, no. But if everything is to be found, you can find everything. You can find all of the entities. So the goal here in Rankine cycle, you have to find all the entities and the comfort to find, let's say, the cycle efficiency. So okay, let's start with the point one. So for point one, okay, for point one here, okay. So for point one, we know that this is a superheated vapor, no, within the superheated vapor region. So since the temperature and pressure are given, we just find the enthalpy and entropy in this table 3. No? So you can find this in table 3 is find 4.10 and 440 degrees Celsius. So you can find enthalpy and entropy. So why did we actually this should be multiplied by 3, no? So why did we need to find the S1 also? The S1 is also needed because this is constant. So this process, no, 1 to 2 is constant entropy. So we will use that for finding point 2. No? Okay, so we're good with point 1. So for point 2, actually it could happen that this will still be superheated, no? But we won't get into that yet. But since we want to find 2, which is usually the wet region, the saturated region, so you want to find all the F and the FGs. No? So find F and FGs for enthalpy and entropy. Okay. So you have to find the fluid and the Hg minus Hf or HFG. So you only need one property for point 2, which is usually pressure. No, but it depends. It could be temperature. You know, you can also use table 1. If temperature is given, sabihin natin dito, if T only is given, you can use table 1. Okay? But it really happens that you will use table 1. It really happens. You will need to use table 2 for 99% of the time. So you found HF and HFG, SF and SFG. You want to now find the X, no, or the quality to find the enthalpy. So this is the end goal here, no? Find the enthalpy. So basically, you already have your S2 because S1 is equal to S2, right? So because this is a constant entropy process. So this is your S1, which is also your S2. And then equate this to Sm plus X SFP. No? So to find X or the quality. So after finding the quality, given your enthalpy, no, or your saturated liquid and saturated gas in the form of HFG, you can find the enthalpy at the exit. Okay, so at this point, you can already find the I cannot find pala. No? Cannot find the network because you need the pump work as well. Okay, so moving on, we need to do the point three. So for the point three, no, so for point three, it is what? No? Saturated liquid. Saturated liquid, therefore it should use still this, no? Actually, this is the same thing. No? So this is HF2. HF2 means 100% liquid, no? Or 0% vapor. So this is 0% vapor, so therefore you should use HF. So HF2 is basically just your HF3. HF3 is also your H3. Okay, so that's it. For point three, actually you can use table 4 for point three. But you only have pressure given, no? We don't know the temperature. To me, we don't know the temperature. So we cannot really find the, we cannot use table 4, no? It's not a problem at this point. So what we have to do here is we can find the VF, no? Or the specific volume. So the specific volume now is still actually at this point, no? Point 1 HF, no? So you just have this given this given pressure. So the inlet of your pump is 0.105. So that will be the inlet condition, which is the inlet. So actually this is also equal to BF2. Okay. So you find the specific volume for finding the pump work. So if you find the pump work, you can also find the HP. Okay. Okay, now after finding the specific volume, sometimes if the specific volume is not given, you can just say 1,000, no? But it is not given, 0.0601,000 meter cube per kilogram. If it is not given or there is no way to find the specific volume, there's some cases like that. No? But anyways, the pressure is given, you can find this specific volume. So the specific volume multiplied by the pressure difference. So the pressure difference here is in terms of kPa, no? We have MPa. We just converted this into kPa. No? So that we will have a unit of kilojoule per kilogram. Okay. So after finding the pump work, we can now find the HP, no? Or the enthalpy at point B. So for the point B, it is just no, using the mass balance. Sorry, not mass balance, but the energy balance. You can find HP by adding the pump work and the fluid enthalpy at point B, which is this. We have 423.4 plus 4.78 is 47.4. So now to find everything. Also for QA, so for QA, this is just H1 minus HP, right? So this is 3305.7 minus HB is 427.4. Okay. So you can find this as, so I hope this is correct now. So 2878.3 kilojoule per kilogram. Okay. For QR code, QR code. So for QR, this will be equal to QR. So QR is H3 minus H2. Oh, yeah, H2 minus H3 pala. H2 minus H3. So this will be 2508.6 minus H3 424.23. Sorry, 4.423.34. So QR is this should be 285.4 kilojoule per kilogram. Then the next one is the network. So the network, there are different ways to find the network now. But since we have QA and QR given, you can say that W net is equal to QA minus QR. So just subtract this two, you can have 792.9 kilojoule per kilogram. Okay. And then lastly, for efficiency, cycle efficiency, this is just the network over QA. So since these two are given, we can just solve this directly. So 792.9 over QA is 287.8.3. And therefore this will be um this should be 27.55%, not 8 percentage. Okay. So that's it for A. All right. So moving on, we have letter B. The same problem. We want to now find the mass flow rate required for the same to have a net output of 30,000 kilowatts. So when we say net output, we're talking about the network now. So to find the mass flow rate, so the net power is equal to the network multiplied by the mass flow rate of steam. So this will be equal to uh, so, uh, the mass flow rate is equal to the power over the work done. So you have 30,000 kilowatts of kilojoule per second over. So the network here is really this should be power. Yeah, so straight yeah. So 792.9. So this should be 37.84 kilogram per second. So kilojoule per second over kilojoule per kilogram. Okay, kilogram per second. Okay, so last one. So same problem, but we're now talking about the Rankine engine. So operating between these limits, compute for the thermal efficiency and the heat rate. So for the thermal efficiency, you need to know the network and DC, right? So we already know the net. Okay. This is the different work pala. No? Okay, this is just for easy pala. So for thermal efficiency kasi of an engine, this is work lang, no? Work of the turbine over PC. So the work of the turbine is just H1 minus H2. So, teka. Yes, H1 minus H2. Yes. So H1 minus H2, and then this will be H2. Ah, what is H1 minus H2 pala. H1 minus H2. So for this rocket engine, to find the efficiency, thermal efficiency of the engine, you can use pH here, for engines. This will be H1, so H1 minus H2. So 3305.7. 3305.7 minus 208. 2508 pesos. 0.6, and then all over 33507. 05.7 minus HF2. HF2 here is also H3 now, so this one. So 423.24. 423.24. So this should be 27.65%. Okay. And then moving on, you have the heat rate. So for the heat rate is just equal to P times 600 over the efficiency, of the engine, thermal efficiency of the engine. Right? Ideal, no? So since it's only ideal, that's only lang yun. Um, hmm. Saka, heat rate lang pala, no? The thermal efficiency din. Okay, heat rate ang naghahanap, no? So we can find this heat rate. Let me check. Ano ba? Okay. 6. 1.2765, di ba? 765. So this will be your heat rate. This is just 3,600 over the thermal efficiency. Okay. Ah, ito. Ito. Ito pala yun. It should be 0. 0.7. For this will be 13,020. So 13,020 kilojoule per kilowatt hour. So let's take note of the units of the three and three. So we are okay, so that's over for example one. Let's move on to another example. Okay, so as the power plant operates on this cycle, the cycle shows on the if the isentropic efficiency of the turbine is 87% and the isentropic efficiency of the pump is 85%, determine A, the thermal efficiency of the cycle, and B, the net power output of the plant for a mass flow rate of 15 kilogram per second. Okay, so this will be a little bit complicated and you will need to find a lot of enthalpies. No? So because we have an actual and an ideal properties here. So as you can see, we start with this superheated vapor at the exit of the boiler. So this point, this will be from 15.2. There is a pressure loss of 0.2 MPa, also a temperature loss, so there is also a heat loss. No? And then for the turbine, there is a isotopic efficiency, we call this isotopic efficiency of the turbine. And then expanded at the condenser. So actually, you have an ideal and you have an isotopic. So you have an actual exit here. So actually, this will be 2 prime, which should be 2 prime, but anyways. So really important here. And then you have 9 kPa here. So there is also pressure loss, no? From 4 to 3. And then 30 degrees Celsius. And then 16 megapascals here. Okay. In this temperature, 30. No, no, no. And then 58.9 and 35 degrees Celsius. Okay, so how do you do this? Now let's get into the first properties that we get. Let's start with drawing pala, no? Drawing muna natin yung PS diagram. So we start with the exit of the boiler. So we have point one. So point one, this is superheated, but there's some minutes superheated vapor. So this is point one. Since there is a temperature drop, there is a temperature drop. So temperature goes lower. Temperature goes lower. Oh, this will also go lower here. So this will be 1 prime now. But since there's also a pressure difference here, so it will go slightly to the left. Yes, it will go slightly to the left. So this will be your 1 prime. So upon expansion in the turbine, there is an isotropic version, no? So this will be the isotropic version straight line. But in reality, it will be an non-isotropic. So this will be your isentropic point, and this will be your non-isentropic point. So this will be 2 prime, this will be your 2. Okay. And then going to the left, you also have an ideal, no? So ideal nuclear, but in reality, there will be pressure drop. No? So this will be a little lower here. Actually, yeah, this will be a little lower here. So the point here for 3, 90 to 30 will be actually this will be at this point, so this will be subcooled. No? So 3 here. I'll make this like 2 prime 2. This will be 3. And then it is pump. No? So pump, so this will be yeah. Should be subcooled. I don't know, this is not 3. Yeah, it should be saturated here, sorry. This should be saturated nga pala, no? So this should be 3. So your process here, um, Okay. So this will the process here will have an isotropic version from pumping, no? Which will be B, and then it's a little bit confusing pala dito, ano? But this will have an actual, no, which is your B prime. Okay, so this will be B and B prime. I'll just write this down like this now. Okay. Yeah. Oops. Should be straight line, no? Straight line then. Yeah. Actually, it should be the idea should be like this, like this, a little bit higher. So this would be the ideal. Uh, but the actual will be a little bit like this. Okay. So we can see already here what are the points. So that will help us in finding the properties is listed table. Okay, so now what can we find first? So what we can find first is actually this prime here. Well, because you have a steam table, no? If you check your steam table, 15 MPa, 600 degrees Celsius at table 2, sorry, table 3, it has a value already, which is this. But for this one, there is no specific pressure that says 15.2. Even the temperature has no specific temperature of 625. So what you have to do is interpolate in between 15 and 15.5 for the superheated table, and then 620 and then 630. So you have a double interpolation at this point, no? To find this specific pitch. No? So in some textbooks, if this is the case, no, in some textbooks only, no? Since this is quite close, they just use the closer one. No? So they will tend to use this one. Just they just need to find one solution. But anyways, uh, we need to find the two, no? So to be exact. For example. So the first thing that you have to do is you have to find the values of 15 MPa and 620 and 630. So 15 MPa, 620, 15 MPa, 630. You have to find these two values, 8. And after that, you have to also find 15 MPa, 620, and 630 there. So after that, the goal here really is 625 and 15.2. So to find this, you need to interpolate this point right here. Using this, no, we can incorporate this one first to find this enthalpy right here. You can also interpolate this. Now after that, find this. So interpolate this two pressure and this pressures and this enthalpies. Then after that, then you can find the enthalpy here by interpolating this and this. So it should be a long one. So we have to check this here to understand how this works. No? So another alternative way to do this double interpolation is to you can find first this interpolation here. So you can use this sorry, this one. You can use this interpolation here to find this. And then after that you can find this interpolation here to find this. Then after that you can also find the interpolation here and here to find this. So it should be the same value or very, very close to that. Okay. So there are two other ways of doing this. So once we found the H1, okay, we're good to go now. So we only need the S1 prime because this is the only one we need now. So this is just for the boiler, this is for the turbine. So for the turbine, we need one prime, no, for the isotropic version because we have an efficiency here. Anyways, moving on to point two, that is in the saturated region or wet region here. So we need to find the HF and the HFGs, the SF and SFGs. Okay. So you can also find already here at this point the BF as well, no? And uh, I think BF only, the specific only. Anyways, let's move on. So to find the actual property at H2 prime, uh, we have the efficiency, right? So the efficiency here will be just what is the output versus the input. No? So the output here is this, right? And this is the input. No? As you can see, maybe let's explain this, that we need the output and the input. Sorry. I think the best way to describe this is for the denominator, this is the ideal, no? Ideal process, and this is the actual process. So to find H2 prime, to find H2 prime, which is this one, you need to find the isentropic H2 first. No? So since H1 is already given, you can find H2. So the isentropic efficiency is given. Then you can find the actual entropy here. So finding this isentropic first, so find natin muna isentropic using the previous method. So using the SFG and SF and S1 prime, you can find the quality, uh, which is 80.37%. So after that, you can find the isentropic enthalpy at point 2. Okay. So after finding that, you can just solve for H2 prime using this isentropic, using this isentropic efficiency. So therefore, the H2 prime will be 2305.6 kilojoules per kilogram. Okay, we're done with point 2. So for point 3, that will be for point 3 that will be finding the VF, no? So the specific volume of point 2 actually, no? So no. If we sorry, ito pala given, no, 9 kPa. So this is an actual process. So we need to find VF3. So VF3 here is an actual process and it's different from 2. So you need to use 9 kPa for the saturated liquid. No? So upon using this, you can find this specific volume and this enthalpy here. Okay. So after that, you can also find the actual pump work. Actual pump work po ito. It should be divided by efficiency. No? Okay. So divided by efficiency to find the actual pump work. So multiplying this by the pressure difference. So the pressure difference between this pump is 16,000 megapascals and 9 kPa. So the units here are in kilopascals, no? Then you can get the actual pump work. Actual pump work ang ipakuha natin. Then you can also find the point B. So the point B here, outlet of the pump, using also the pump work. So the actual pump work plus H3, no, is equal to HB. Ayan. So this will be okay, this will be 18.99 plus 183.29. Okay, so we got HB as well. So to find HB prime, this is a subpool, no? Compressed, no? Compressed liquid or subpool. So B prime. So B prime here, so we need to also do a double interpolation, no? Pero in some cases, no, usually textbooks, they just do this. But you need to do the double interpolation as well. So given 15.9 and 35, we don't have 15.9, we don't have 35. So using table 4 for some liquid, you need to find HB prime. Okay. And then after that, you get the HB prime. You need to solve for the thermal efficiency, for this problem. So the thermal efficiency is the network over the input heat. No? So we know that the network is equal to, actually, kiri pala muna. No? So the heat added, no, as you can see in the heat balance here, you have H1 minus HB prime. So you will just use H1 and HB prime to get QA, which is 3485.4. And then for the network, that will be the turbine work and the pump work. So That will be the difference between the two. We can also do this. Okay, this should be fine now. So you have this, and then you can find the network. So to find the efficiency network over QA, you have 36.1%. Okay, and then for the net power output, so if you have a mass flow rate, you can also find the power output, which is just multiplied uh, by the network. So the network is 1257.71 multiplied by 15 kilograms per second. So this will be 80,865 kilowatts or 8 megawatts per 8.9. Okay, so that's it for this example. So maybe I should explain. Good luck.